So we'll now start discussing the operational semantics of C++ like language, for which we had also discussed semantic rules, semantic analysis rules. So what are operational semantics? Recall that operational semantics basically trace the execution of the program on an abstract machine. And there are two types of operational semantics. There's small step and big step operational semantics. And we'll be discussing big step operational semantics. Recall that we also said that all these different types of operational semantics are essentially equivalent. They're just different ways of representing the same properties. And so we just choose one of them, which is big step operational semantics, primarily because they are easy to understand and easy to formulate. Okay, so how are we going to specify the operational semantics? We're going to specify them as logical rules of inference. And we have already been introduced to the idea of logical rules of inference, or inference rules in short, when we were discussing about typing. And our typing judgment was of the form that under a given context, where context could be, for example, the scope or the variables that have been defined, the environment, the current object, and so on, a certain expression has a type C, right, or something like that. So this was the judgment in typing when we were discussing typing rules and semantic analysis. Very similarly, we are going to use an evaluation judgment to specify the operational semantics. And the evaluation judgment is going to look like the following, somewhat like the following. Under a given context, again, the context is going to capture the environment, which will include the scope and things like that. It is true that E evaluates to value V. So in the given context, E evaluates to value V. That's what this notation stands for. Under a given context, it is true that E evaluates to value V. Okay, so for example, maybe we have one such rule in our operational semantics database of rules, which says that if under a given context E1 evaluates to 5 and under the same context E2 evaluates to 7, then under the same context E1 plus E2 evaluate to 12. All right, and now this rule seems really straightforward, and also it's a very specific rule. We are using specific values of the constants 5 and 7. Typically, we'll just use placeholders for these values, so that we can have one rule that covers a lot of different values that are possible. Also, this kind of typing or evaluation judgment is saying that even is a valid expression that can be evaluated to a legal value, and the value is going to be, let's say, an integer 5. All right, and in this case, the value is going to be an integer 7, and so on. Also, there is this context that is on the left-hand side of the turnstile operator, and it's really not doing much in this particular rule, because it's just saying that the context should be the same for evaluating E1 and E2 and E1 plus E2. Also, this rule is saying that during the evaluation of E1 plus E2, the context does not change. Okay, so as we are already familiar, an inference rule basically encodes a lot of information in a very small amount of notation, and so it's very important to carefully read an inference rule. Now the question is, when we are talking about evaluation, what should constitute the context? All right, so one thing that immediately strikes us is, what if E1 has references to some variables, let's say X or Y or things like that? So one thing that the context should give us is what are the current values of these variables, right? And so, for example, one thing that the context should involve is mappings from variables to values. For example, I could have E1 to be X and E2 to be 1, and only this expression X plus 1 can only be evaluated if the context involves a mapping for X. All right, and this would basically tell you what is the way to evaluate X plus 1, assuming that you can already evaluate X and you can evaluate 1. And similarly, you can make bigger expressions out of smaller, you can evaluate bigger expressions out of smaller expressions. So it's just like we were talking about typing judgments. These rules here, the E1, E2, basically are placeholders for any expression that can be pattern matched to this particular rule. In general, in particular, this rule is basically for the addition operator. So we're also going to label these rules. For example, this is for the addition operator because inside the when we are going to traverse the abstract syntax tree, we are going to see what operator is the top level operator, and based on that we are going to invoke the appropriate evaluation rule, just like we used to invoke the typing rule during semantic analysis. Okay, so for C++ like languages, once again, we are not really talking exactly about C++ because that's a much bigger language and has lots of different subtleties that we are not discussing in the lecture modules. But we have a language which kind of resembles C++, so that it is familiar to us, the syntax is familiar to us, but it's not too complex, right? It has simple semantics, it has simple syntax, and so on. So for C++ like language, we track variables with their values, and to track variables and their values, we have two things. One is the environment, which says where in memory a variable is. So if I say a variable x, then the environment is going to say that x is a variable that lives at location, let's say 100, or in the memory space, or 10,000, or whatever. Or in general, you're just going to keep it abstract and say x is a variable that represents the location L, right? And then there's a store, which is the actual memory, all right? And which basically says what is in the memory. So for example, x maps to location L, and then we can look into the store and say what are the contents of memory of the store at location L, all right? And so to track the context, we need two maps. One is the environment, which maps a variable to a location, and second is a store, which maps location to values. Now, why do I need two maps? Why couldn't I have just done with one map? I think it will become very clear when we look at some examples. So environment maps variables to memory locations, and store maps memory locations to values. All right. Okay. So a variable environment maps variables to locations and keeps track of variables that are currently in scope. All right. So only those variables are present in the environment which are in the current scope. And for statically scoped languages, this is determined by what the static scoping rules say, right? So that's coming through the scope resolution. So, and also tells us where those variables are. So for example, one example of an environment is E equals A mapping to L1 and B mapping to L2. So here, these are A and B are variable names, right? So these are just names of variables. Okay, and the L1 and L2 are locations, right? So these are locations in memory, okay, and so in memory or store. All right. Okay, so that's the variable environment. Notice that this has no notion of value so far. It's just mapping names to locations. And that's just coming from, for example, scoping rules and things like that. And then a store maps these locations to values. For example, a store S could be L1 maps to 5 and L2 maps to 7. So 5 and 7 here are values, and L1 and L2 are locations. Now, why do I need different environment and different scopes? So different store, because the environment basically is just mapping things that are currently in scope, whereas the store is mapping everything that may or may not be in scope. For example, there are many reasons why you would want to separate these things in a language like C and C++, because, for example, what about star x, right? So star x is not a variable, but star x has some, star x refers to a location. So first of all, x refers to a location, let's say L. Then star L basically means you dereference L and you get a value and you treat it as a new location. And then that's what star L basically refers to, right? And so star x is not really a variable name. X is a variable name, but star x is not a variable name. And so to be able to, so the memory state is more than just the variable names. The memory state is a lot of other things. For example, through dereferencing or through aliasing. For example, two or more expressions may refer to the same variable, to the same location. For example, star x and y may refer to the same location. And so the environment won't be able to capture something like that, but the combination of environment and scope and store will be able to capture that for us. So for example, if star x and y point to the same location, then in the environment, x would point to some location, let's say Lx, and y would point to some location, let's say Ly, and then store would point to point Lx to Ly, all right? And so that way, in this particular configuration, I have star x equals y, because y is pointing to Ly in the environment. So this is environment, by the way. So y is pointing to Ly in the environment, and x is pointing to Lx, but in the store, Lx is pointing to Ly. So Ly is the value, all right? And so, these kind of pointer based syntax is not possible to do just with mappings from variables to values. You need the idea of locations, and then you map variables to locations and then locations to values. All right. Moreover, we are going to have another notation to define to basically represent updates to the store. So for example, I can say S open brackets 12 for L1 basically means that whatever is the store, in that store just assign the value 12 to location L1. All right. So more formally, if I call this whole thing, this whole memory here as S prime, then S prime defines a store such that S prime L1 equals 12. So because that's the overriding thing. So 12 has been assigned to L1, but everything else which is not L1, so for everything else that is not L1, S prime L equals Sn. All right, so that's the definition of S prime. So for example, if S was L1 mapping to 5 and L2 mapping to 7, so these are the only two locations that have been mapped in the store so far, then S prime would map L1 to 12 and L2 to 7. So it will leave L2 unchanged, and it will map L1 to, it will update the mapping of L1 to 12. So that's the idea of this particular notation, S updated such that 12 has been replaced at L1. Okay, all right. Also notice that when I say store represents memory, store is actually not the memory as in the hardware sense of memory, which is mapping an entire address space from, let's say, 2 to the power 32 addresses to bytes. It's actually a very abstract way of representing the store, and the abstraction is that it's just a map from some location IDs. So in this case, the location IDs are L1 and L2. We haven't even said how are these location IDs represented? Are they represented as integers? Are they represented as strings or something else? We haven't really said anything about that. But we just said that, there are some location IDs, and those location IDs are mapping to values in this way. Once again, we are not really saying how those values are representing. We're just saying it's an integer called 5, right? It's an integer called 7. And so we don't really say anything, and that's the whole idea of specifying semantics at an abstract level, so that different implementations can implement it in different ways. For example, if I have a machine that has only 16-bit address space, it is possible to implement this language on that, because the abstract machine, the operational semantics will not really specify how big L1 should be. It just says that there is some location ID called L1. It really doesn't say how big L1 needs to be, and so on. All right. Now, what are the values in a C++ like language that we're going to consider? So one of the types of language values are just simple values like integer 5, and I'm going to use the notation int 5 to represent an integer 5. Similarly, I'm going to use float 5.0 for a floating point 5.0. Or a value could also be just a location, for example, L1. Right? Now, once again, because I have left the idea, I'm not really specifying the exact bit representation of how a floating point is going to be represented. Is it going to be some IEEE format based representation, or is it going to be a fixed point representation? We haven't really said anything about that. We haven't also said anything about how an integer is represented. Is it 2's complement or something like that? And similarly, we won't say how the location is represented. We're just saying that it maps to a location, but we haven't really said whether its location is 32 bits, 4 bits, 16 bits, 8 bits, whatever, right? So that's the values are also abstract, just like locations are abstract in our semantics. Okay, then there are kind of object values, or more complex values, or compound values, if you will, and these are for structures and classes. And in our language, we are going to assume classes, just like C++. And so classes can have multiple attributes, which are the fields of a class, just like in C++. And so I can say there's a class X that has attributes A1, A2, ... AN. And a value is basically an object of type X whose attribute A1 maps to location L1, attribute A2 maps to location L2, and so on, and attribute AN maps to location Ln. So this is also a value, all right? So this is important. I would like to emphasize this. This is also a value. Once again, I haven't really said what is the representation of the value. Is it going to be contiguous? Are the attributes going to be contiguously laid out? Recall that when we were talking about code generation for objects, we had different ways of how we could lay out the attributes so that it becomes easier for us to implement code generation. But at this point, at this level of abstraction, we are really not talking about how the attributes are laid out. We really don't care. It's left abstract, so that different implementations are free to choose whatever layout they like. We are only saying that, look, there are some locations that have been decided for A1, A2, and so on. And those locations are just abstract quantities L1, L2, and Ln. We are not really saying anything about how these locations are represented or how these things are packed. So X is the class of the object, AIs are the attributes, and LIs are the locations where AIs are stored respectively. All right. So, and this is also a value. So for example, my store could map a particular location, let's say L, to a value which is this entire class object, right? So this whole thing represents a value, an object value, and a store could map a location to this value, and that would be perfectly fine. And we won't really, we don't have to worry about how big is the value. Does it overlap with other locations or not? Because for us, locations are just abstract quantities, and there's no notion of overlapping or how they're represented in memory or things like that. All right. So notice that the layout of the object is not specified at all. Right? And there are many other things that have not been specified at this level of abstraction, and that's the whole point of representing the language semantics, so that you keep things as abstract as possible, and yet give a precise and complete description of what the language is supposed to mean. All right, then there is a special value called void, just like we discussed void when we were discussing typing rules. And the semantics of void, recall when we were talking about typing rules, we said void is the super type of all other types, and that's an assumption that we are making in our language, which is not necessarily true for C and C++. And we will basically assume that no operations can be performed on this value void. So void was a type when we were discussing typing rules. Now when we are discussing evaluation rules, void is not just a type, but void is also a value. All right. And void is a special value, and void value basically means it's a nothing value, and which basically means that there are no operations that can be performed on it. And so concrete implementations are free to use any representation for the void value. For example, they may decide that they're not going to use any space whatsoever in memory for the void value, and that's also okay. Or they may just use any random bit pattern for the void value, and that's also fine. It's just up to the language implementer to basically decide how he or she wants to represent void. But it's important to know that void is also one of the values in our language. Okay, so this is what our evaluation judgment will look like. S0, E, and S would represent our context. All right, so these three things would represent our context. And under this, I'll talk about what each of these three are, S0, E, and S. But under this context, it is true that E evaluates to value V. So expression E evaluates to value V, and recall that V, the value could also be the void value, or it could be an object value or a simple value, and a store S prime. So E does not just provide you a value, but it also provides you a new store S prime. And in what context is E evaluated? E is evaluated in three different components of the context. One is this object S0. So recall that in an object-oriented language, an expression can be evaluated in the context of a particular class and its object. So for example, I could say this dot something in the context of an object, and then this is supposed to mean something. And to be able to capture the idea of this, we need to have the notion of what is the object under whose context I'm currently executing this expression or evaluating this expression. So S0 is the current object, also this object in C++. And so we're going to call that S0 or S0. Then given the current variable environment E, so E is the current variable environment that represents the current scope, and we have discussed this. The current variable environment maps variable names to locations. Locations are abstract. And then a current store, which is the current store of memory, which is mapping locations, abstract locations, to abstract values, right? So we have already discussed E and S. The only thing new here is S0, which is supposed to represent the current object under whose context this particular evaluation E is being evaluated. And this judgment E colon V comma S prime is supposed to mean that if the evaluation of E terminates, then the value of E is V and the new store is S prime. Okay, so notice there are two things here. One is we are assuming that the evaluation of an expression is going to evaluate to a value V, and we are also assuming that saying, not assuming, that during the evaluation of E, it is possible that the store gets updated from S to S prime, and so the new store is now S prime. Okay, so few things to note here. S0 is the current object, this object, and in whose context we are evaluating the expression. E is the current environment under which we are evaluating the expression. So one thing to note here is that neither S0 nor E are changing during the evaluation of the expression. This is just the semantics of a C++ like language, that while you're evaluating the expression, it's not possible for you to change the context under which you were executing the expression, evaluating the expression. In other words, you can't change this object under which there are other ways to do it, but not through just the evaluation of an expression. Similarly, you cannot change the environment, scope environment, just through the evaluation of an expression. Recall that we change the environment when we see declarations and stuff like that, and that's only when we get into a new scope or things like that. And we're going to see rules which change the environment, but the evaluation of an expression does not change the environment. However, the evaluation of the expression does change the store, and that's how we represent the side effects of an expression evaluation. So example, we say that assignment is an expression. So we can say x equals y, and x equals y returns a value, but it also updates the store, because it updates the memory, because what it does is it changes the location of x, which is lx, the contents of the locations of x, which is lx, in the store, right? So all the side effects are represented by updates to the store, not through the updates to the environment or to the current object. All the side effects are only represented through the updates to the store, and that's what we know about C++ like languages anyway. They don't really change the environment, they don't really introduce any new variables, but they can change the state of the memory. And that's what S prime is supposed to represent, and we also call them side effects of evaluating the expression. Finally, notice an important subtlety. If the evaluation of E terminates, then, all right, so it's very important. This is the antecedent of this particular evaluation judgment. This is saying that this statement that E evaluates to V is only true if the evaluation of E actually terminates. If evaluation of E does not terminate, then this rule is not saying anything. All right. So it's very important to notice that this is saying if the evaluation of E terminates, only then we can say that the value of E is V and the new store is S prime. This is going to become more evident when we are going to talk about actual evaluation rules and see why. And when we are reading those rules, it is important that we kind of keep saying this. All right. So we keep saying if the evaluation of E terminates, then E evaluates to V and updates the store to S prime. If we don't say this, then some of our evaluation rules will not look sound, will not look correct. And so it's important to basically keep saying this if the evaluation of E terminates then. Now, an obvious question here would be, what if the evaluation of E does not terminate? Does that mean, what is that supposed to mean in our language, in our C++ like language? Well, the answer to that is going to be more nuanced. First of all, we're going to discuss big step operational semantics. So in big steps operational semantics, it is important to have such an antecedent that if the evaluation of E terminates, because we basically represent the value of a larger expression in terms of the smaller expressions, and that can only be done by assuming that things are terminating and the value was actually computable. So this is coming to the faulting problem and computability. If we instead use small step operational semantics, which would just change one part of the program state in one step, smaller steps, then it would have been possible to express non-terminating evaluations as well more easily, but we are using big step operational semantics. Typically, languages like C and C++ would say that if a program is non-terminating and it is not, and kind of it has, and syntactically it is not possible to figure out that it is non-terminating. For example, it's not like non-terminating using a while one or a for colon, semicolon, which is forever loop. Then it's actually undefined behavior in C. So that kind of a program is illegal in C. In any case, that's a bit of a digression. But in our particular language, we are going to assume we are only going to give semantics to that part of the language which is terminating. So only terminating programs will be given semantics in our particular language. We are going to assume that in our language, if a program is non-terminating, then it has no semantics. All right. What do I mean by a program has no semantics? Well, it basically means that the program can be implemented in any which way you like, because there are no well-defined semantics for the language. All right. And so the code generator can basically assume that the program is terminating.